Hello, everybody. We are live. Welcome to the third session of Health AI University. Don't be intimidated by that number, the third session. Each of these are meant to be self-contained. So if you missed the previous sessions, which were on the impact of AI in healthcare and patient engagement and how to understand and when to use machine learning, you'll still be able to follow along with this very important session just fine. So the reason I say very important is that this one gets into, like, we understand what these projects are and what they're capable of, but how do we know they're actually useful? How do we know they're actually any good? And there's some metrics that we're going to be discussing that ultimately the idea behind running this session is that you could be able to walk away with those metrics, walk away with an understanding of when you're evaluating AI decisions or decisions for patient engagement and outreach that will use things like propensity models. Then you'll have the right questions to ask to know whether one model is going to perform better or even perform at a level that's useful for the outreach that you're trying to do. So that's ultimately what we want you to come away with. We're going to do that using simple explanations, no heavy math or anything like that. There's no technical background required. And we're going to give you a cheat sheet and an interactive tool that you can play with to better intuit these concepts. And of course, you'll have the video if you ever want to repeat it, but ultimately you'll have tools and sheets to start being able to ask these projects, ask these vendors that you're interacting with about, hey, how do we know whether or not you're performing well? Reintroduction, just in case you hadn't seen us before. I'm Chris Hemphill. I, as Director of AI and Client AI and Operations, I do data science projects on the client-facing side, and the mastermind behind it all and the data science operations that we have here, Joe Schmid, our Chief Technology Officer. So on the next slide, what we're going to be welcome back to the series. Again, emphasis for this session is on being able to understand whether different approaches or whether different models outperform, and arm you with the right types of questions to ask people that are presenting these options and solutions to you. And Joe will take it away with beginning the session.
Awesome. Thanks, Chris. Welcome back for those folks joining us again. And for the new folks, welcome. Like Chris said, these sessions are independent, so don't feel like you missed anything that's going to be a problem for today. We've got a really fun one for today. I think it was super fun putting this together with Chris. For me, session 3 is the most fun. We're going to get into some real details. We're going to arm you with a lot of knowledge that a lot of folks don't have, all around understanding model performance. And we've got so much material to cover today. I want to actually dive right in. So we're going to break things into 3 big buckets. We're going to talk about the fundamentals around model performance. We're going to talk about metrics that help you measure that performance. And we're going to talk about score thresholds and trade-offs. And just like Chris said at the beginning, we hope you'll leave today's session armed with this understanding that you can go ask the right questions. You can really evaluate model performance as you work with the coming wave of models in healthcare, that you've got a much better understanding of how to measure those and how to put them into practice. So with that, a quick recap from last session. So this was our kind of wrap-up slide for machine learning. So how do we teach machines with data? We talked about using inputs on the left. So how do we take, say, patient data? How do we take labels and answers? In this example, we're looking at something like cardiovascular surgery. So how do we label the patients for the machine to learn and to train models? And then we looked at how a model lets you make predictions on new patients that the model hasn't seen before to make recommendations. And we had our kind of very simple diagram that wraps up the machine learning approach in conceptual form, where we feed in data and the answers, also known as labels, and our computation produces a model that lets us make future predictions. So with that, what we're going to do today is not worry about that process, but we're actually going to pretend that we already have a model trained. And this model is going to predict this yes, no type of scenario. So in the example we just looked at, cardiovascular surgery or not, meaning a patient's a good candidate for that or not. This could be any other thing, could be recommendations for breast cancer screening or orthopedics or bariatrics. And then what we want to know is we want to know how well the model works. So how can we assess the kind of performance that we're going to get, and what is that performance? We're going to understand that in detail. We're going to test it on labeled data, meaning that data that has the answers assigned that the model hasn't seen before. And we'll show you how that works. And this is really going to help you understand how models perform and how you can assess them. The one caveat for today is for this particular session, it's pretty detailed. It's not difficult. It's really simple concepts, like Chris said, no complex math, nothing like that. But it is detailed, so we recommend you pay close attention. I'm a serial multitasker, so I know how that goes. But for this session, we did want to let you know ahead of time that you'll get a lot more out of it if you just pay close attention for the next 25 minutes or so. All right, with that, so let's break down the process. So step one, we're going to collect our test data. And we're going to make this a very small set of data just so that you can understand it in detail. Your real data sets might have millions of patients, but for our simple example to understand this, we're just going to have, say, 10 example patients. And we're going to have the real answers assigned, positive, negative. Again, this could be something like cardiovascular surgery or not. And that's what we're going to start with. So that's our really simple 10-item test set. The next thing we're going to do in step two is we're going to feed that data through our pre-trained model. And you see two new columns in our little grid here. The third column we now see is the model gave us a prediction. And for our simple positive negative case, we see those. And because we know the real answers, we can assess the model. We can say, was that prediction correct? And you can see most of the cases, the model did get this right. And in 3 cases, it was wrong. So really simple, very, very basic concepts. So now let's build upon that. The first thing we could say is, well, how accurate is the model? And if we had kind of a simple kind of cursory view of that, we could just count up the yeses and nos in our was the model correct column, and we could come up with an accuracy metric. We could say it got 7 out of 10 correct, and that the model accuracy is 70%. Now, there's 2 big problems with this. The first one is there's different ways to be wrong, and they may not be equal, and we're going to actually break those down. And then the second thing you might be wondering, where are the scores? We know machine learning is all about math, and we expect numbers. So why aren't we seeing any scores or numeric values? And we'll show you how that's going to go too. So this might be the most important slide we see today. What you're seeing is a grid called a confusion matrix, but we can understand it in just plain English terms. What it's saying is there are only 4 cases that correspond to these 4 squares for our predictions compared against the truth or the real answers. And what we like to do is we like to walk across this from left to right, where we take our prediction. And so let's start at the top left and say, let's take cases where we predicted, our model predicted a positive. And then we can just walk across and say like, oh, the first square that we get to is we predicted positive and the real answer, the truth was positive. So we got that right. And we call that a true positive, and we color it green. Going across to the right, we can say we predicted positive for this row, and over on the top right, the real answer, the truth was negative. We got that one wrong, and we call that a false positive. Now we can do the same thing for our second row. So now we're changing what we predicted. We predicted a negative, and we go to the square on the bottom left, and we see the column is that the truth or the real answer was positive. So we got that one wrong, and that was a false negative. And then our last case, again, we predicted negative, but in the bottom right, the column is the real answer, the truth was negative. And we got that one correct as a true negative. If you find yourself getting confused with true positive, false positive, just substitute some synonyms and it'll start to make sense. So we could say correct positive. We could say right answer positive. For false negative, we could say we got it wrong negative, things like that. And this will make much more sense. So if you've made it to this point, give yourself a pat on the back. Everything we're going to do from here on out just builds on these 4 simple cases. We've introduced some new terminology. You'll get the hang of true positives and false negatives and things like that. But you can always go back to this basic confusion matrix as a reference. Everything we're going to do is just going to build on these 4 simple cases. So if you made it to this point, it's half the battle. So now, interestingly, let's talk about some use cases where we might go and put a model into practice. And let's think about 2. The first one we'll talk about is, let's say we're going to do proactive outreach by email, and our emails are going to be pretty generic. Let's say for cardiovascular surgery, we're not going to email a patient and say, oh my gosh, we're worried you're going to have a heart attack right away, but we're going to email them with the benefits of cardio care, we might email them a health risk assessment for them to better assess their care. We might offer them services like easy ways to book consultation appointments and things like that. And for that particular use case, we can observe the relative costs about emailing someone who's not a good candidate and the cost of missing somebody who is a good candidate. And our assessment is for a use case like this, there's a fairly low cost to emailing somebody who might not be the best candidate, meaning they're going to get a pretty generic email about cardiovascular services and an HRA. So not a lot of harm done by that, but there would be a higher cost if we missed candidates who really do have a higher risk. We'd want them to know about these services and have these options. So in this case, we could say we generally want low false negatives. We don't want to miss those good candidates, and we could accept false positives. It's okay to email people who aren't the highest risk. So then let's compare this with another use case in a different industry. Let's talk about something like credit card fraud detection. Well, I think everybody's had the experience of having their card deactivated. We've got to go update your recurring payments, and it's a really big hassle when you get notified by your bank that they need to deactivate your card and send you a new card. So for banks, there's a really high cost to deactivate a customer's card. And there's a medium cost to fraud. You might think that they're really sensitive to suffering the costs of the fraud itself, but there's a lot higher cost to disrupting good customers. So in this case, we could say they want really low false positives. They don't want to turn off people's cards that they don't need to, and they can accept some false negatives. They can cover the cost of fraud if they miss actual fraud cases. So just ways to think about applying this to actual use cases. So now let's keep building on this. Given that we understand those 4 cases, we can add another column to our results for that type of result, and we could classify our different ways we can be right and wrong into the 4 that we saw. So now on the right side, we have a more sophisticated view of accuracy. Previously, we had this really simple view of accuracy that just said 7 out of 10 were correct. Now we can break those down. For our 7 correct, in our simple little 10 example scenario, 6 were true positives, 1 was a true negative. So we got those right. And out of the 3 that our model got wrong, 2 were false positives and 1 was false negative. So now we've got a more sophisticated view of the accuracy. So let's keep going and build on that and ask, where are the scores? So we talked about the numbers. So for our simple case, let's just give it some scores. These are just made up for our example. We can assign scores, and these happen to go from 1 to 0. So they're decimals like 0.9 or 0.8. And we've got some scores we can work with. But something happened when we assigned the scores. Where are our predictions or our answers? Before we said our model was guessing yes or no or positive or negative, but now we just have these numbers. So this is another very fundamental concept that we'll introduce. And this is a really important slide. And so we need to take these numbers and we need to pick a number so that scores above that are considered as positive. And so let's just draw a line. Let's just put a line and say that everything 0.5 or above, we're going to consider that positive. And what that means, of course, is that scores below that are now considered negative. And this is this concept of a score threshold. The models are trying to assign the positive cases very high scores and negative cases very low scores. But as practitioners, we get to set this threshold. And we're going to talk about the trade-offs that come by setting that threshold. But really important concept to say that when models make predictions, there are numeric scores, and we use thresholds to indicate which scores above that are going to be positive and which scores below that are negative. So again, if you made it to this point and you understand thresholds, give yourself a pat on the back, but we're actually going to show this in a little more detail. And let's talk about it in the concept of a campaign. Let's take our simple 10 case example, and let's say we decide to use a score threshold of 0.3. So everything above 0.3 is going to be considered a positive case. We would go do outreach to those patients. Those would be our candidates to do the outreach above the threshold that we chose. We could have a more selective threshold. Let's say we picked something like 0.7. So we're emailing fewer folks. It's a tighter grouping. And we notice that in this simple example, we didn't get any wrong. So we have a higher accuracy, and we're actually going to give you some more specific terminology for that. But in this case, we can have a smaller group with perhaps a higher accuracy, and we could do outreach to those. So let's actually play with this interactively. We've got a nice little tool we built, just a simple spreadsheet, and we can see this visually. So what the spreadsheet does is it lets us pick a threshold, and then it kind of updates in real time, the results. And we can change this to be, say, really low. Let me make it 0.2. And we can see that that indicates everything 0.2 or above. Our model is going to say it's positive. We can make an assessment of did we get it right under that scenario? And we could play with this threshold. And we could see how the results change with that. And so you get a sense for what that allows us to do. So now let's jump back to our slides and let's understand the impact of the threshold. So you remember our confusion matrix, our simple 4 conditions that we can be right or wrong under. And now we saw our simple view of accuracy and our more sophisticated one. And we could see how that more sophisticated view maps to the confusion matrix for those 4 cases. But now what we want to do is look at those numbers, not just for the individual cases, but across our entire population. And we can do that visually. And that visual looks like this. And I'll kind of explain what you're seeing here. So on the left side, those are the relevant elements or the correct answers. So where you see the filled in circles, you can think about those as your positive cases for the truth of the real answers. On the right of this particular visualization, you see the open circles are the true negatives, the ones that really are negative examples for our real answers. And then the visual, the way this works is the circle indicates what the model selected. So the model selected these ones that are circled, and we could split those into 2 cases inside our circle. We could say the model got some of those right. Those were true positives, and you see those over here on the left half of the circle, colored with the green background, and it got some of them wrong, and those were false positives. And you see that colored with the red background on the right. And so those are our 4 cases that come from our truth, confusion matrix, laid out across an entire population. And so now we can use this visual to understand specific metrics that data scientists use to assess models. So let's break this down. So the first term that we're going to introduce is the word precision. And what does that mean in plain English? It answers the question, how many selected items, how many items did the model circle, are relevant or correct answers? And you can see visually the calculation of precision using grade school math. The numerator is going to be your left half of the circle, the ones the model said were true positives, over the total size of the circle. Your denominator is the number of items in the circle. And that is precision, a fundamental metric that data scientists use to assess models. Let's talk about the flip side, recall. And recall answers the question, how many relevant items are selected? And you see the visual is going to be different. So what is this dark green area outside the circle? It's the one the model should have said were positive, but it didn't. So those are those false negative cases. And our simple grade school calculation, our numerator stays the same, and our denominator is everything on the left side, the real positive answers or relevant elements. And you can see the actual formula. We can just lay it out here, which maps to our colors here. True positives divided by our true positives plus our false positives. That's precision. And don't worry about memorizing these. You can always go look these up later. And recall, same true positives in our numerator, but it's true positives plus false negatives, the green outside the circle. And so these, you've now just learned the very fundamental concepts that every data scientist use to assess model performance. We're actually going to look at how that works in practice. But let's talk about what makes for high or low precision or recall. So let's take our same view and our formula we just saw. And there's something that really sticks out in this simple formula. You notice that you have the same term in the numerator as you do in the denominator. So the only thing that's varying is the false positives. And we could say if our false positives were really low, let's say the model did a great job and it was perfect, and the false positives were 0, we know the same element divided by the same element is 1. So we're going to have a really high precision because precision and recall values range from 0 to 1. And we could say the flip side. If we had a lot of false positives, so we've got a high number for that element, our precision would be close to 0. So now you start to develop this intuitive sense of false positives are really the driver of how good your precision is. And let's do the same thing for recall. We can look at our simple formula and we can understand what makes it high or low. We have the same, notice the same pattern. It's true positives on the top, true positives on the left of the bottom, just like you saw over here. And the only thing that's different for recall is we're using false negatives in our denominator. So same type of pattern. If we had really low false negatives, that means our recall is very high. We're correctly getting all of the true answers or positive cases. And then if our false negatives are high, we're going to have very poor recall, meaning we're missing a lot of those positive examples. So great. With this lens, we looked at changing the threshold for specific values, but now let's go do something different. Let's jump back to our spreadsheet and let's look at the threshold across all the different values we can use. And so if we look at our spreadsheet, this was a view we had before, and just as a refresher, I can change the threshold manually. But let's go to another tab where Chris and I have laid out ahead of time all the different thresholds. So you see our same 10 simple examples, our simple scores. But what we've done is we've just made columns for every relevant threshold, and we've calculated the results there. And we can scroll out and see we've done this for all the relevant values that we could use as a threshold. And great, we've got all our cases. And what we can do is we can calculate our different metrics for recall and precision under those different thresholds. And what we can do with these results is we can plot them. So let's plot them on a chart. This is a very famous view called a receiver operating characteristics curve. And in a second, we'll tell you a little bit about the history of this. On the left side of the y-axis, we have our true positive rate or recall. On our x-axis, this varies just a little bit from what you've seen. It's a slight variation on precision called false positive rate or fallout. It's a little bit different formula. It gets us a view that is just a classic way to look at things, but the same concepts that we're using. And we can plot all those points, and we can just draw those in blue, and they make kind of a stair-step pattern since we don't have very many examples. And for comparison, we're going to put some red dots on there and draw a line for kind of our random guessing case. If we had a model that was just flipping a coin, its performance would look like this. And of course, we want to have much better performance than random. And so we have just made by hand a ROC curve, or a receiver operating characteristics curve. And how did we do it? We calculated our performance at various thresholds, and we just put those points on a chart. Really simple. And we can jump back into our slides, and we can take a look at that. And we can draw the line so that we see the actual curve, which isn't much of a curve in this case because we only have a few examples. And you can see that that fits this classic ROC curve pattern that you see if you've run across model performance. This is one of the things that would be incredibly common to see is a ROC curve that indicates the model performance under many thresholds. And so we've just made one by hand. So with that, let me jump out as an aside and tell you a little bit about the history, just a minute on this. This came out of an effort in World War II to develop radar, especially around detection for bombers coming into Britain. And you could imagine that there would be false positives in these early radar systems. The radar would give you a signal, and maybe there's a flock of birds flying by versus a bomber, and the operators had to tune these systems. And they did the exact same thing that we just did, is they recorded accuracy under certain thresholds, and they plotted those points out on a graph, and they came up with this ROC curve to help them pick thresholds to say, above this, we're going to consider it a bomber, and we're going to take action. Below it, we're going to consider it a flock of geese, and we're not going to scramble to react. And that was the early work. There's a great link that covers some of this history. For those interested, I recommend going to check that out. Kind of goes through the history of receiver operating characteristic curves and some of the development in some nice detail. So let's jump back into our ROC curve. The next thing we can do is we can calculate another very common metric called the area under the curve. You'll see this as AUC or ROC AUC. And because our curve is so simple, we can actually do this by hand. And we can split our curve to measure the area under it into two simple rectangles. We can just draw a line there. And we can do this manually. We know this particular rectangle is 0.43 high, it's 0.33 wide. We can multiply that out. This other big rectangle is 0.86 high and 0.67 wide, and we can multiply that out. We can add them together. And for our silly little 10-item example, our area under the curve is 0.72 out of a possible 1. So reasonable performance. Random guessing would be 0.5, so we have better performance than that. but we would ideally want to get closer to 1. And we like to see ROC curves certainly above 0.8 for many of the imbalance sets. And we'll show you one of these. We have quite a bit higher, often in the high 0.9s for imbalance cases in healthcare. We'll show you one of those later. So now let's actually interactively play with changing the threshold on a ROC curve. And so I'm going to show you 2 examples. I really love this visualization that we put together that lets you see this interactively. So let me explain what you're seeing on the screen. On the left side, you see our ROC curve, just like we plotted by hand. The same axes, we have true positive rate on the left or y-axis, and you want to be high. You want to have a high true positive rate, so you want to be up around the top left. And our false positive rate along the bottom, and you want to have obviously a low false positive rate, so you want to stay on the left side of this plot up here. And our curve gives us the various thresholds we can pick with the associated performance metrics. We're calculating precision and recall for each point. And then on the right side, you just see counts. We're going to do this with a really simple vertical bar graph, and we see counts of our 4 conditions back to our confusion matrix. And then on the bottom is our threshold. And here's the coolest part. I can just grab this slider and everything changes in real time. So let's walk through changing this. Let's start with a very high threshold. So we can make that right up at the top at 1, and we can walk this down. And what we're going to do is we're going to go, you can see the curve, the shape of it means we're going up on our true positive rate. Our true positive bar out on the right is going to start to go up quickly. And we're picking up some false positives, not very quickly because we're not moving to the right as we go. So let me do this interactively. So let me creep it up, and you can see our selection based on this threshold. You can see the blue dots. We're going up, up, up. You can see the sizes of the bars on the right changing. We're picking up some false positives as we go. You can see that increasing. We're pretty balanced here. And then as you go, the curve starts to roll over. So the curve starts to move out to the right. And as we have low thresholds, you'll see the false positives go up quickly. That means we're moving out to the right on the chart. And so you can see if I go all the way to the bottom with a threshold of 0, where we're guessing all negative or all positives, you can see what that means in terms of we're catching all of the ones that we should. So our recall is perfect, but of the ones that we're recommending, only about half are correct. You can see that in the true positives and the false positives. What you might do as a practitioner is you might use something like this to set your threshold. As a data scientist or a marketing outreach specialist, you might work with data scientists to select a false positive rate that achieves your objectives. Maybe you want to maximize recall. Maybe you want to get a really high recall while trying to minimize false positives. So maybe you would run at something like maybe 0.9 recall, meaning you're catching 90% of those positive cases you want. And still the results you recommend are 80% correct with a 0.79 precision. And you can see sometimes curves are sensitive to you're losing that precision as you go. Maybe you wanted a more targeted, smaller set, but really high scores. So you wanted to optimize for precision. Maybe you want to run at 90% or 0.9 precision, but you're still missing a lot of good examples. So you can make those kinds of trade-offs. Now, the numbers you're seeing in this particular visualization are just made up. This is just fake simulated data. Let me show you a real one. Let's take the same view, but this visualization uses results for one of our real machine learning models. This is a bariatrics model trained on real client data. One thing that sticks out is you see that the results counts are way higher. So we've got 3 million patients in this set, and the true positives are very low. This is a real needle in a haystack type problem. So we don't have many cases that we're trying to find out of millions of patients. You can see the curve has good overall performance. It's right high and tight in the top left corner. And I can pick that, I can adjust those thresholds. So maybe for something like this, I want to run at maybe 80% recall, but I lose precision in that case. And you can see that curve start to pull away from the left side. So this gives you options. I hope that was a useful visualization, and seeing the interaction helps drive home some of these concepts. So let me jump back into the slides and wrap up. I know we're just about out of time. So today we talked about the fundamentals of model performance. We introduced the confusion matrix and our 4 cases around true positives and false negatives in those 4. We talked about metrics like precision and recall and AUC and calculated those by hand. We talked about score thresholds, and we interactively observed some of the trade-offs there. So we hope you come away much more armed with understanding the basics of model performance. This should really serve you well in a world where AI is coming to every industry and there will be models all over. We hope that this will be something that you can use throughout your career. So I know we probably don't have time for questions, Chris. Any words of wisdom for our wrap up?
Sure thing. Thank you. And sadly, we don't have time for questions, but we do have email addresses. So feel free to reply. What we're going to do is send out a guide that helps that identifies the questions to ask of the projects or vendors that you might be evaluating. So that way you have the knowledge that Joe helped intuit into something that you can actually take out and start using for the different things that you might be evaluating or working on today. That's also going to come with that interactive tool that Joe is sharing. So keep an eye out for that. And big thank you for everybody who stayed on with us. Next couple of sessions that we have, Virtua Health, Ryan Younger, the VP of marketing there, will actually be talking about how to tell data stories. So the concept that's being addressed there is, okay, so we put these models in place. We've done some great things with them, but how do we communicate that throughout our organization? How do we communicate success and results throughout our organization? And then the final session coming up in Health AIU is on, it goes into more specifics on tactics and strategies to navigate projects that you have coming in. But again, thank you very much and look forward to seeing you soon.
Thanks, everybody.